Let's solve this classic transistor circuit problem. We're asked to find IB, IC, and VCE, and we're told the transistor is operating in active mode with a current gain beta is 50. These kinds of questions show up all the time in exams, so getting good at them is a must. If you're not totally confident with transistor basics yet, I highly recommend checking out our beginner-friendly transistor tutorial. It's packed with clear explanations and animations to help everything click. Link in the description. This is a NPN transistor circuit, and we can tell because the arrow on the emitter is pointing outward. That little arrow is your cheat code for recognizing NPNs. Now let's label some key parts of the circuit to make things easier to understand. First, IB is the base current. It flows into the base terminal of the transistor. Then there's IC, the collector current, which flows into the collector terminal. And finally, VCE is the voltage across the collector and emitter terminals. Since we're working with a common emitter configuration, there's one more crucial voltage to keep in mind, VBE. That's the voltage between the base and the emitter, and it plays a major role in how the transistor behaves. Now on to the other components in the circuit. The voltage source connected to the base is called VBB. This one controls the base current, IB. The voltage source connected to the collector is labeled VCC. The resistor connected to the base is RB, and the one connected to the collector is RC. Once we've got the labels correct, the rest becomes much easier to solve. Now in this problem, we're told that the transistor is operating in active mode. But what exactly does active mode mean? To answer that, let's take a quick look at the three main operating regions of a BJT transistor. This helps us understand how IC and VCE behave in different conditions. First, there's the cutoff region. This is when the transistor acts like an open switch. Even if you increase VCE, no current flows from collector to emitter. That's because there's no base current. IB is 0. In this case, VBE is equal to VBB. But since there's no current through the base resistor, the transistor is off. That means IC is 0 and VCE is equal to VCC. If that sounded like gibberish, don't worry. Check out our previous transistor video where we explain it all with visuals. The link's in the description. Next up is the saturation region. Here the transistor behaves like a closed switch. Current flows freely from collector to emitter, and VCE drops to nearly 0. The base emitter voltage, VBE, stays around 0.7 volts. We can calculate the base current by applying Ohm's law across the base resistor. When using transistors as switches, we typically operate them in just these two regions, cutoff for off and saturation for on. Finally, there's the active region, and this is the mode we're dealing with in our problem. In the active region, the transistor acts as an amplifier. Both VCE and IC are non-zero, and VBE stays constant at about 0.7 volts. The base current IB can be calculated using Ohm's law across the base resistor. But here's the cool part. The collector current IC isn't just random. It's determined by the base current and the transistor's gain. That gain is called beta, and in our problem, it's given as 50. So, IC is equal to beta times IB. This means the transistor is amplifying the tiny base current into a much larger collector current. Once we have IC, we can also find VCE by subtracting the voltage drop across the collector resistor, RC, from VCC. So with all that in mind, let's start solving the problem step by step. In our problem, we're told the transistor is operating in active mode, so, like we mentioned earlier, we can confidently say that VBE equals 0.7 volts. Now let's find the base current, IB. Take a look at the base side of the circuit. We're dealing with a resistor RB, which has a value of 200 kilo ohms. It's connected between the voltage source VBB, which is 4 volts, and the base terminal. The base sits at 0.7 volts because of the VBE drop. That means we can calculate the voltage across the resistor. And since we know the resistance, we can use Ohm's law. IB equals V divided by R. That's 3.3 volts divided by 200 kilo ohms, which comes out to 16.5 microamps. So the base current IB is 16.5 microamps. Simple, right? Just Ohm's law in action. Next, let's find the collector current, IC. Since the transistor is operating in the active region, we know that IC is equal to the gain multiplied by IB. The gain, also known as beta, is given as 50, and we already calculated IB as 16.5 microamps. So IC equals 50 times 16.5 microamps, which gives us 825 microamps, or 0.825 milliamps, and there you have it. IC is 0.825 milliamps. Now finally, let's calculate VCE, the voltage across the collector and emitter. To do this, take a close look at the output side of the circuit. If we rearrange the layout in our minds, we can see that the supply voltage VCC is shared between the collector resistor and the transistor itself. That means VCC equals VRC plus VCE. We don't know VCE yet, but we can figure out VRC using Ohm's law. We already found the collector current IC to be 0.825 milliamps, and the collector resistor RC is 100 ohms. So VRC equals IC times RC, which is 0.825 milliamps times 100 ohms. That gives us 82.5 millivolts, or 0.0825 volts. Now we apply Kirchhoff's voltage law. VCE equals VCC minus VRC, that's 6 volts minus 0.0825 volts, which gives us VCE equals 5.9175 volts. So, the collector emitter voltage is 5.9175 volts. And just like that, we've completely solved the problem. See you in the next one.